Hello, ladies and gentlemen. I hope everyone is doing well. My name is Mubarak, and this is a presentation for our class project for the machine learning class for the spring 2023. And our project is about assessing machine learning algorithms used in classification of breast cancer tumors. And I do this along with my colleagues, David, Fagana, and Yusuf. And breast cancer is a cancer that sits in the cells of the breasts, and its seriousness depends on whether the tumor is malignant or benign. So we diagnose this type of cancer by using a microscope, and the microscope is used to examine a sample of the affected breast area. And after obtaining this data, we use machine learning models to help and predict whether the tumor from this area is malignant or benign. So in our project, we are using different machine learning algorithms to classify these breast tumors as either malignant or benign, depending on the features. Of course, we know that breast cancer is really a big problem. It has been a big problem from a long time ago, and trying to find the best way to detect it early and accurately is really very important. That's why it's very important if we find machine learning really useful especially by professionals, by healthcare professionals, to detect this type of cancer so early and accurately. So we care about this, and the best way of getting this would actually of getting the diagnosis right would bring a lot of improvements to this type of diagnosis. So we have a data set that we are using for this problem, and we got this data, then pre-processed it. Then we did exploratory data analysis, feature selection. Then we split the data into training and test data sets. And because the four of us, each of us used a different model. So on the same data, we tried different models to see which one works best. And after each one of us selected the model, the next phase would be training it and evaluating it. And depending on the model, cross-validation was done to prevent like overtraining. And then, of course, deploying the model. We, like I said earlier, we are using a data set from it's called the Wisconsin breast cancer data set. And this is basically a data set that has information about the nuclei of the breast cancer cells. There's so many features that were measured, and then they were classified as either malignant or benign. So our target in that data set is either malignant or a benign tumor in comparison with the other features of the data set. Of course, like I said before, each one of us ran a different classification model. Uh, my colleague ran a logistic regression. Another one ran neural networks, support vector machines, and k-nearest neighbors. So with that, I'm going to hand over to my colleague Fagana to talk about the model she used for the classification. Thank you very much.
Hello, everyone. Thanks so much, Mubarak. As Mubarak mentioned before, so in our case, the goal is to use logistic regression to predict if a tumor is malignant or benign based on the attributes of breast cancer cell nuclei. So as you see, the dataset consists of 569 instances with no missing values. It contains 357 benign cases and 212 malignant cases. Also, the dataset includes various features related to the nuclear of breast cancer cells. During the processing phase, we renamed columns and selected a few features for visualization purpose. Then we created a histogram of the target variable and a scatter plot matrix to examine the relationship between selected features. We found no missing value in the dataset. And can you go next slides, please? And to prepare the data for modeling, we dropped the ID and diagnosis columns and encoded the target variable as 1 for malignant cases and 0 for benign cases. Then we split the data into training and testing sets using the Square library. And next, we trained a logistic regression model using the training set and made predictions on the test set. To evaluate the model performance, we used various metrics, including accuracy, precision, recall, F1 score, AUC, ROC, classification report, and confusion matrix. And the model achieved an accuracy of 0.9766, which is real good score. And also we also performed 10-fold cross validation, and we found the mean accuracy is 0.9543. Can you go next slide, please? So as we see that, we can say that logistic regression also one of the powerful and straightforward method for breast cancer diagnosis, because we got really good accuracy score, which is 0.9766. Now I'm gonna stop here, and my colleague David's gonna continue. Thanks so much.
Yeah, and I'm going to talk about the neural network. As deep learning nowadays are drawing a lot of people's attention. It's getting a really high accuracy on training models and getting the predictions right. And so we're trying neural networks as well. For data preparation, we firstly split up the data into a ratio of 10 to 1 for training and testing dataset. And then we use encoder. For this experiment, we use a really simple encoder called label encoder from sklearn. Basically, it is by transferring every single features to a one hot array and add them up all together and forming a matrix. And that is our inputting embeddings for this data for this neural networks training. For the model structure, we have a couple different layers. For the input layer, we have 30 input nodes representing every single one of the features. And we use the ReLU activation functions at the end of the first layer. And then we have two hidden layers, each with 16 nodes, and we're using also the ReLU activation functions as well. We also add the dropout layers at every single hidden layer to just prevent overfitting. The percentage of the dropout layers is 0.1. So basically 16 nodes for every single hidden layer. We randomly drop out one or two nodes from every single one of the hidden layer. And for the output layer, we have only one node to represent, either to represent whether the result of prediction is good or bad of the cancer. We use the sigmoid activation function at the end. The neural network actually shows a pretty decent result. By using the confusion matrix, we get the 98.24 accuracy. Next slide. Yeah, for the future work of our experiment about the model side, firstly we do the hyperparameter tuning. For the hyperparameter we are using right now, we have 150 epochs. We have the batch size of 100%. We also split the training set and testing set by 9:1. All those numbers could be changed in order to improve the accuracy of the model. So that's one thing. For the ensemble learning, we can use techniques like bagging, boosting, or stacking. We can possibly use different models as well. By combining all those models, we can make a better prediction on our dataset. For the model structures, we're using ANN right now, but there are a couple more alternatives. For example, the CNN, convolutional neural network, and RNN, recurrent neural network. Based on my experience, I feel like the CNN is a little bit better because for the features that we have in our model, in our data set, there are not a lot of sequencing data. They are all independent to each other, so it's better to use CNN instead of RNN. For the data preparation in our future work, we can use feature selection, like by manually select the best feature for the data prediction, for the model prediction. And we can also use transfer learning, saying that we can find a smaller or a bigger models which are doing similar things, have similar functionalities. They are trained on similar data, or they are trained on similar data set. So by fine-tuning those model, we can actually use less data to make a higher prediction. So that so transfer learning could be a way. And we can also just improve our data set by having more data, or like by using techniques to make up data by using the data augmentation technique. Yeah, so that is the neural network.
Thank you, David. So one of the other algorithms that was used for classification of this data was the support vector machine. And of course, this is a commonly used machine learning algorithm for both classification and regression. And it works by finding the optimal hyperplane, which separates the different classes of the data points, and the hyperplane chosen to maximize the margin between the two classes. And this is done by finding the distance, of course, between the hyperplane and the nearest data point from each of the classes. And this SVM is good for binary classification, especially like in cases like in the one we have right now, for classifying both like benign or malignant tumors. In SVM, during this project, of course, we had to process the data, like earlier stated by my other colleagues, remove the missing data, then normalizing the data and splitting it into both testing and training sets. So we know that SVM uses a kernel function to transform the data during its classification or regression. So this can be a linear, a polynomial, or RBF, or a sigmoid kernel function. The choice of the function will depend on the nature of the data and, of course, the complexity of the decision boundary. So on this data, we use the 4 kernels and to run the algorithm on the data. And then we evaluated the accuracies and their performance. And we reported, of course, what the kernel that produced the best accuracy, as shown here in this graph. Sigmoid, of course, performed really bad, and the best of them was the linear, which we considered and then we came up with an average accuracy of 95.61%, which is pretty good, but it could be better using other algorithms or picking the parameters in the same algorithm, which was not really done. But generally, the accuracy was 95.61%. I would like to call upon my other colleague, Yusuf, to talk about the algorithm he used on the data set. Thank you so much.
Thank you. Hello, Professor and TA and all. I am going to go over the K nearest neighbors algorithm. Look into this as a definition. It's known the K nearest neighbors algorithm, also known is non-parametric supervised learning classifier, which uses proximity to make classification or prediction about the grouping of individual data point. To go a little bit detail, is estimating the likelihood that the data point will become member of one group or another based on what group the data point nearest to it belong to. If you look to the picture, the K nearest neighbor tries to determine what group a data point belong by looking at the data point around it. Next slide, please. Building the K nearest, looking to the K nearest neighbor, we built the model consists only storing the training data set. To make the prediction for new data point with the findings, the closest data point in the training data set. K neighbors classification, we study the nearest neighbor, which is the closest training data point to the point we want to make a prediction for our output for training data training point. So before we start training our data model, we look to the correlation, each columns, as you can see the display. So you could see that all the features are not same. So what we needed is to comprehend more. We count how many neighbors belong to each class, and again, predict the most common class. Next slide. We consider applying K-nearest neighbor algorithm using the skip learning. First, we split our data into training and tests to evaluate generalization performance. Then we set the parameters, the number of neighbors to use. Then we fit the classifiers using the training. For the K-neighbors classifiers, this means storing data set so we can commute the neighbors during the prediction. To make prediction, one test data we call predict method. For each data point, the data test set, this commutes its nearest neighbors in the training set and find the most common class. We evaluated how our model generalized, and we call the score method for the test data together. As you can see, the accuracy outcome for the training set is 94%. For the testing set is 93. So on the chart, you could see the shows the training data set accuracy on the y-axis. Again, on the sitting number of neighbors, that's for x-axis. The y-axis is the accuracy, and the number of neighbors is x-axis. We can also recognize some overfitting, underfitting. We consider a single nearest neighbor. The prediction on the training data is perfect. The test set accuracy for using single neighbor is lower than when we use more neighbors. In predicting that using the single nearest neighbor lead to the model to become more complex. On the other hand, we consider 10 neighbors. The model is too simple and performs even worse, but still the best performance in somewhere in the middle, as you can see the chart. But that shows the around 6 neighbor. But still, our performance is acceptable because the outcome is 93%. Next slide. So in conclusion, all the algorithm that we used, k-nearest is the lowest outcome. We got it 93%. SVM, support vector machine, the accuracy outcome is 95%, 95.6%, but it's slightly less than the logistic regression and neural network model. The logistic regression, it's the second highest. We got it outcome of 97.7%. Our neural network has the highest test accuracy, which is 98.2%. Shows the best performance among the model evaluated. Thank you so much, Professor and TA and all. We thank you your time, and thank you.